the largest telescope ever flown, launched into deep space. Recently, we got a look at some captivating images as Webb peers back toward the origin of everything.
There are many planets out there waiting to be visited. However, one problem common to them is that humans cannot survive for a long time on them. This is why the recent news of the James Webb Space Telescope discovering a fully habitable green planet is amazing. What is the name of the planet and what convinced scientists that this green planet could be habitable? Keep watching this video to find out. WASP 96 is a star that has a lot to offer for exoplanet enthusiasts. It is a yellow dwarf star similar to our Sun but slightly cooler and older. It is located about 1,150 light-years away from us in the southern constellation of Phoenix. WASP 96 was discovered by the Wide-Angle Search for Planets, or WASP, a project that uses robotic telescopes to look for planets that transit in front of their stars. WASP is an amazing project that explores the wonders of the universe beyond our solar system. WASP is an international consortium of several academic organizations that use robotic telescopes to specifically look for exoplanets, which are planets that orbit other stars. WASP uses a method called transit photometry, which detects planets by measuring the slight dip in brightness of a star when a planet passes in front of it. This way, WASP can find out the size and orbit of the planet and sometimes even its mass and atmosphere. WASP has 2 observatories, one in the northern hemisphere and one in the southern hemisphere, that cover a large area of the sky and monitor millions of stars simultaneously. WASP has been operating since 2006 and has discovered over 150 exoplanets so far, making it the most successful ground-based search for transiting exoplanets. And WASP also collaborates with other telescopes and instruments to confirm and characterize the planets it finds, such as the JWST, the most powerful space telescope ever built. And to date, WASP has revealed a rich diversity of exoplanets, from hot Jupiters to super-Earths, from water worlds to cloudy giants. WASP has also found some of the best candidates for habitable planets, or planets that could support life as we know it. WASP is a remarkable project that has greatly advanced our knowledge and understanding of exoplanets and their diversity. Now, a transit is when a planet passes between us and its star, causing a slight dip in the star's brightness. By measuring this dip, astronomers can infer the size and orbit of the planet. Now, WASP 96 has at least one planet, WASP 96b, which is a gas giant about half the mass of Jupiter and slightly larger in size. It orbits very close to its star, only 1/9 of the distance between the Sun and Mercury, and takes only 3.4 days to complete one orbit. This makes it very hot, with a temperature of about 1,285 Kelvin. And WASP 96b is one of the first exoplanets to be observed by the JWST. The JWST launched in 2021 and started observing exoplanets in 2022. Now, water is essential for life as we know it, so finding it in other worlds is always an exciting discovery. And that's exactly what happened when NASA's JWST observed WASP 96b, a hot, puffy gas giant orbiting a distant Sun-like star. WASP 96b is one of the most extreme exoplanets ever discovered. It has a mass less than half that of Jupiter, but a diameter 1.2 times greater, making it much puffier than any planet in our solar system. And the closeness of its orbit to its star means that WASP 96b is scorching hot, with a temperature greater than 1,000 degrees Fahrenheit. And because of this, you might think that such a planet would have a very thin or even no atmosphere at all, but you would be wrong. WASP 96b has a thick atmosphere that can be studied by observing how starlight filters through it when the planet passes in front of its star. This technique, called transmission spectroscopy, reveals the presence of specific gas molecules based on tiny decreases in the brightness of precise colors of light. Using this technique, JWST's near-infrared imager and slitless spectrograph, or NIRIS, measured light from the WASP-96 system for 6.4 hours as the planet transited its star. The result was a stunning spectrum that showed the distinct signature of water, along with evidence of haze and clouds that previous studies of this planet did not detect. This was the first time that JWST detected water in an exoplanet atmosphere, and it did so with unprecedented precision and detail. The strength of the signal that the JWST detected hints at the significant role the telescope will play in the search for potentially habitable planets in the coming years. And JWST's powerful new view also shows that WASP-96b is more complex than previously thought, with a dynamic and diverse atmosphere that may hold more surprises for future observations. Finding water on WASP-96b is a remarkable achievement that showcases JWST's amazing capabilities and opens new horizons for exoplanet research. It also reminds us of how diverse and fascinating the universe really is, and how much we still have to learn about it. But how did water end up on such a hot and hostile planet, and what does it tell us about the origin and evolution of WASP-96b and other similar worlds? To answer these questions, we need to look at the history and chemistry of this extraordinary exoplanet. WASP-96b actually belongs to a class of planets known as hot Jupiters, which are gas giants that orbit very close to their stars. These planets are thought to have formed further out in their planetary systems where water ice was abundant and then migrated inward due to gravitational interactions with other planets or their stars. And as they moved closer to their stars, they experienced intense heating and tidal forces that inflated their atmospheres and altered their compositions. And the presence of water on WASP-96b suggests that it retained some of its original icy material during its migration, or that it accreted more water-rich material later on from comets or asteroids. However, water is not the only molecule that can form in such high-temperature environments. Other gases can also be produced by various chemical reactions in the atmosphere. The relative abundance of these molecules depends on many factors such as temperature, pressure, radiation, and metallicity. For example, at high temperatures, water tends to break down into hydrogen and oxygen, while at lower temperatures, it can condense into clouds or raindrops. Similarly, at higher pressures, methane can be converted into carbon monoxide or carbon dioxide, while at lower pressures, it can escape into space. The detection of water on WASP-96b has several implications for the search for life on exoplanets. First, it shows that water can exist on a wide range of planets, not just Earth-like ones. Water is a common molecule in the universe, and it can form in various ways on different types of planets. For example, water can be delivered by comets or asteroids, or produced by chemical reactions in the atmosphere or interior. Water can also be retained or lost depending on the planet's mass, gravity, temperature, and magnetic field. Second, it shows that water can be detected with high precision and detail by the JWST and other telescopes. Water is one of the key molecules that astronomers look for when they study exoplanet atmospheres, because it can indicate the presence of liquid water on the surface, or at least a habitable temperature range. Water also plays an important role in the chemistry and climate of exoplanet atmospheres, affecting their stability and diversity. Third, it shows that water can reveal more information about the planet's history and evolution. Water can provide clues about how the planet formed and migrated in its planetary system, how it interacted with its star and other planets or moons, and how it changed over time due to internal or external processes. Water can also influence the formation and composition of clouds and haze in the atmosphere, which can affect the planet's appearance and observability. Fourth, it shows that water can inspire new questions and challenges for exoplanet research. Water can raise new possibilities and puzzles about the origin and nature of life in other worlds. For example, could life exist in the atmosphere of a gas giant like WASP-96b? Could life adapt to extreme conditions of temperature, pressure, radiation, or chemistry? Could life leave any detectable signs or biosignatures in the atmosphere? And another stunning thing detected on WASP-96b is the presence of carbon dioxide. Carbon dioxide is a common molecule in the universe, and it can have various effects on the atmospheres and climates of exoplanets. But how did JWST detect carbon dioxide on WASP-96b, a hot, puffy gas giant orbiting a distant sun-like star? And what does it tell us about this planet and others like it? JWST detected carbon dioxide on WASP-96b using a technique called transmission spectroscopy, which reveals the presence of specific gas molecules based on tiny decreases in the brightness of precise colors of light. This technique works by observing how starlight filters through the planet's atmosphere when the planet passes in front of its star or transits. During a transit, some of the starlight is eclipsed by the planet completely, causing the overall dimming, and some is transmitted through the planet's atmosphere. Because different gases absorb different combinations of colors, researchers can analyze small differences in the brightness of the transmitted light across a spectrum of wavelengths to determine exactly what an atmosphere is made of. JWST used its NIRSpec for its observations of WASP-96b. NIRSpec is one of JWST's 4 scientific instruments, and it can measure light from 0.6 to 5 microns in wavelength, covering most of the infrared spectrum. NIRSpec can also observe multiple objects at once using a micro-shutter array that can open and close tiny shutters to select which sources of light to measure. JWST observed WASP-96b for 6.4 hours as the planet transited its star. The result was a stunning spectrum that showed the clearest evidence for carbon dioxide ever detected in an exoplanet atmosphere. The signature of carbon dioxide appeared as a small hill between 4.1 and 4.6 microns in the spectrum, indicating that some wavelengths of light in that range were absorbed by carbon dioxide molecules in the atmosphere. This part of the spectrum is particularly sensitive to carbon dioxide, as well as other key molecules like oxygen, methane, and water, which are not immediately obvious in the WASP-96b spectrum, but which should be detectable in other exoplanets planned for observation by JWST. Now, the detection of carbon dioxide on WASP-96b by JWST has several implications for the search for life on exoplanets and the rest of the universe at large. First, it shows that JWST can detect carbon dioxide with high precision and detail on a wide range of planets, not just Earth-like ones. Carbon dioxide happens to be one of the key molecules that astronomers look for when they study exoplanet atmospheres because it can indicate the presence of photosynthesis, respiration, or volcanism on the surface, or at least a habitable temperature range. And carbon dioxide also plays an important role in the chemistry and climate of exoplanet atmospheres, affecting their stability and diversity. Second, it shows that JWST can reveal more information about the composition and formation of the planet by detecting carbon dioxide and other molecules. Carbon dioxide can provide clues about how the planet formed and migrated in its planetary system, how it interacted with its star and other planets or moons, and how it changed over time due to internal or external processes. Carbon dioxide can also influence the formation and composition of clouds and haze in the atmosphere, which can affect the planet's appearance and observability. Third, it shows that JWST can inspire new questions and challenges for exoplanet research by detecting carbon dioxide and other molecules. Carbon dioxide can raise new possibilities and puzzles about the origin and nature of life in other worlds. For example, could life exist in the atmosphere of a gas giant like WASP-96b? Could life adapt to high levels of carbon dioxide or low levels of oxygen? And could life leave any detectable signs or biosignatures in the atmosphere? Fourth, it shows that JWST can compare and contrast different planets by detecting carbon dioxide and other molecules. Carbon dioxide can help us understand how different planets are similar or different from each other and from Earth. For example, how does carbon dioxide vary with temperature, pressure, radiation, and metallicity? How does carbon dioxide interact with water and other gases? How does carbon dioxide affect the habitability and detectability of planets? And another huge discovery made by the JWST on WASP-96b is something you might have taken for granted: clouds. In truth, clouds are common features in the atmosphere of planets both in our solar system and beyond. But how did JWST detect clouds on WASP-96b, a hot, puffy gas giant orbiting a distant sun-like star? And why did earlier studies conclude that this planet did not have any clouds? JWST detected clouds on WASP-96b by using a technique called transmission spectroscopy, which reveals the presence of specific gas molecules and particles based on tiny decreases in the brightness of precise colors of light. This technique works by observing how starlight filters through the planet's atmosphere when the planet passes in front of its star or transits. During a transit, some of the starlight is eclipsed by the planet completely, causing the overall dimming, and some is transmitted through the planet's atmosphere. Because different gases and particles absorb different combinations of colors, researchers can analyze small differences in the brightness of the transmitted light across a spectrum of wavelengths to determine exactly what an atmosphere is made of. When the JWST observed WASP-96b last year for more than 6 hours as the planet transited its star, the result was a stunning spectrum that showed the distinct signature of water along with evidence for haze and clouds that previous studies of this planet didn't detect. The spectrum also showed the first clear evidence of carbon dioxide ever detected in an exoplanet atmosphere. The signature of clouds appeared as a flattening or smoothing of the spectrum at certain wavelengths, indicating that some wavelengths of light were blocked or scattered by cloud particles in the atmosphere. Clouds can affect the transmission spectrum by obscuring or reflecting some of the spectral signatures of molecules radiating beneath them. The detection of clouds on WASP-96b by JWST is a surprising discovery that contradicts previous observations from other telescopes, such as Hubble and Spitzer, which suggested that this planet had a clear atmosphere. This discrepancy could be due to several reasons, such as different viewing angles, different wavelengths of light, or different atmospheric states. For example, clouds could vary in time and space due to changes in temperature, wind, or stellar activity. Alternatively, JWST's higher sensitivity and resolution could have revealed features that were missed by previous instruments. And another possibility is that clouds could form at different altitudes depending on the wavelength range, as suggested by a recent study using computer simulations. The study found that clouds could form on WASP-96b at different pressures, depending on the temperature and metallicity, the amount of elements heavier than hydrogen and helium of the atmosphere. And the study also predicted that JWST observations would be affected by clouds, where within even the near-spec wavelength range the cloud top pressure varies by an order of magnitude. This hot gas giant was discovered by a team led by Nikolai Nikolov, an astronomer at the University of Exeter in the United Kingdom, using the European Southern Observatory's Very Large Telescope in Chile. The team identified the exoplanet's atmospheric makeup by watching it pass in front of its host star and measuring how the planet and its atmosphere affected light from the star. The composition of a planet's atmosphere affects the light that astronomers can measure as it passes past its host star. This results in a spectrum which is similar to a unique fingerprint. Clouds typically obstruct the light emitted by a planet and alter the spectrum that researchers may observe from Earth. And what the scientists discovered was an exceptionally obvious signal for the element sodium on WASP-96b. Because clouds generally mask such signs, the clarity of this spectrum revealed that there are no clouds at all in this planet's atmosphere. According to astronomers, it was the first indication of a totally cloudless planet and the first time a planet with such a distinct sodium signature has been discovered. WASP-96b is the first cloudless planet identified thanks to its unusually clear signature. As the first of its kind, the exoplanet was now regarded as a benchmark for characterization. Furthermore, sodium levels in WASP-96b's atmosphere are comparable to those seen throughout our solar system. Sodium is the seventh most abundant element in the universe, and scientists have long assumed that big gas giants had sodium-rich atmospheres. However, there has never been such convincing evidence to corroborate this theory. Therefore, the scientists felt their observation of WASP-96b strengthened their understanding of gas giants. And yes, as already mentioned, exoplanets can have clouds and haze in their atmospheres, just like Earth. Clouds and haze are both made of tiny particles that scatter or reflect light, but they have different origins and effects. Clouds form from the condensation of gas into liquid or solid droplets, while haze forms from the chemical reactions of gas molecules into solid or liquid aerosols. Clouds and haze can affect the temperature, pressure, and chemistry of an exoplanet's atmosphere, as well as its appearance and reflectivity. Clouds and haze can also make it harder to detect other molecules in the atmosphere, so astronomers need to take them into account when studying exoplanets. And clouds and haze can be made of different materials depending on the conditions of the exoplanet. For example, clouds on Earth are mostly made of water, but clouds on other planets could be made of ammonia, methane, sulfuric acid, or even sparkling minerals. And haze on Earth is mostly made of organic compounds, but haze on other planets could be made of hydrocarbons, sulfur, iron, or silicates. Clouds and haze are actually common in exoplanet atmospheres, but their properties vary depending on the temperature, pressure, and composition of the planet. So how do clouds and haze affect exoplanets? Clouds and haze are both made of tiny particles that scatter or reflect light, but they have different origins and effects on exoplanets. Clouds form from the condensation of gas into liquid or solid droplets, while haze forms from the chemical reactions of gas molecules into solid or liquid aerosols. Clouds and haze can affect the temperature, pressure, and chemistry of an exoplanet's atmosphere, as well as its appearance and reflectivity. Clouds and haze can also make it harder to detect other molecules in the atmosphere, so astronomers need to take them into account when studying exoplanets. And the JWST detected water, carbon dioxide, haze, and clouds in the atmosphere of WASP 96b, revealing new details about this planet and others like it. But how do these discoveries help us find out what is going on other exoplanets? For example, what do these discoveries say about finding artificial lights on Proxima b, a rocky terrestrial planet orbiting the nearest star to the Sun, Proxima Centauri? Proxima b is a potential candidate for hosting life as it lies in the habitable zone of its star, where liquid water could exist on the surface. However, Proxima b is also likely to be tidally locked, meaning that one side of the planet always faces the star and the other side is in perpetual darkness. And so detecting artificial lights on the dark side of Proxima b could indicate the presence of a civilization that uses LED light technology or mirrors to illuminate their cities. And to find artificial lights on Proxima b, scientists need to use a technique similar to what JWST used on WASP 96b, transmission spectroscopy. This technique reveals the presence of specific gas molecules and particles based on tiny decreases in the brightness of precise colors of light. This technique works by observing how starlight filters through the planet's atmosphere when the planet passes in front of its star or transits. During a transit, some of the starlight is eclipsed by the planet completely, causing the overall dimming, and some is transmitted through the planet's atmosphere. Because different gases and particles absorb different combinations of colors, researchers can analyze small differences in the brightness of the transmitted light across a spectrum of wavelengths to determine exactly what an atmosphere is made of. And artificial lights are also sources of light that can affect the transmission spectrum. If artificial lights are present on the dark side of Proxima b, they would add some extra brightness to certain wavelengths of light that pass through the atmosphere. The type and intensity of artificial lights would determine their spectral signature and detectability. For example, if artificial lights have a similar spectrum to commonly used LEDs on Earth, they would produce a broad emission peak of around 0.6 microns in wavelength, corresponding to green light. And if the artificial lights would have a narrower spectrum that matches the total artificial illumination on Earth, they would produce a smaller emission peak of around 0.5 microns in wavelength, corresponding to blue light. But the detection of artificial lights on Proxima b depends on several factors such as their brightness, contrast, distribution, and variability. For instance, if the artificial lights were too dim or too similar to natural sources of light, such as stars or auroras, they would be hard to distinguish from background noise. And if artificial lights were too bright or too different from natural sources of light, they would be easy to spot, but also suspicious and potentially misleading. A recent study estimated that JWST could detect artificial lights on Proxima b with 85% confidence if they reach 5% of the natural dayside illumination. However, this requires optimal performance from JWST's near-spec instrument and favorable observing conditions. If not, though, then future observatories like Louvois might be able to detect artificial lights on Proxima b. And so the discoveries that JWST made on WASP-96b provide insights into finding artificial lights on Proxima b by showing us how to use transmission spectroscopy to probe exoplanet atmospheres and identify potential signs of life or technology. They also show us how diverse and complex exoplanet atmospheres can be and how much we still have to learn about them. They invite us to keep looking and learning with curiosity and wonder.